last, but only in name, is FGC Plasma Solutions, co-founded by CEO, sort of did that backwards, Felipe Gomez del Campo, who will tell you about his technology. He is developing a technology that uses plasma to increase efficiency in combustion systems that are hard to replace otherwise. So I'll let you tell them more. Everybody give him a round of applause.
Thanks, Adria. I know I'm the last thing between you guys on a break, but I talk really, really fast, as everyone reminds me, so hopefully that'll make things easier. As Adria said, I'm Felipe Gomez del Campo, the founder and the CEO of FGC Plasma Solutions. Basically, we're working to improve combustion across a wide variety of systems using plasma. But what I'm going to highlight here is our applications to aviation. Because in aviation, fuel is an airline's largest operating expense. So airlines spend over $30 billion of fuel a year, and this goes up about 2% per year with increasing passenger traffic. And there's also tough regulatory pressures from the EPA, ICAO, and other international regulators. So airlines, engine manufacturers, and really the whole industry are anxious to do anything they can to reduce fuel consumption. They do everything from waxing the leading edges of wings to remove bugs and reduce drag, to replacing heavy maps and charts with iPads, because that saves a little bit of weight. Because of this, the technologies that you have are already really good, especially if you look at engines. But jet engines are designed to operate at cruise and to never, ever shut down. At off-design conditions, the story isn't as good, right? So there's still improvements that you can make to engines at low power conditions, and that's where we come in. We have a plug-and-play plasma-assisted fuel injector, say that 3 times fast, which you can put into jet engines and essentially help them reduce their fuel consumption at low powers. Our technology could potentially yield a decrease in fuel consumption of between 1% to 5%, which might not sound all that significant if that's what you get driving in your car. But if you're an airline, that could save over $600 million a year for the US airline industry. And that's also equivalent to a 20 million metric ton decrease in CO2. So it doesn't sound like much, but for this industry, it could be very significant. Now, we're not the first ones to think of using plasma to improve combustion in jet engines or gas turbines or any other system. This is something that's been researched pretty extensively at various universities, national labs, and engine manufacturers. But we are the first ones to figure out how to combine these fundamental plasma science and plasma combustion ideas and put them into a fuel injector that you could actually put into a jet engine. So how do you solve the electrode durability challenges? How do you put the plasma in exactly the right place? And how do you combine this geometry into something that you can retrofit easily into an engine? We have a US patent issued on the technology, as well as a couple other filings, and this patent is also granted in a couple European countries. Now, as far as what this could look like to an end user, if you took a typical 737 on a short-haul flight, say 90 minutes, and retrofitted it with our technology, this could save them about $6 million over the life cycle of the aircraft. At a cost of about $1 million to the aircraft, this is pretty similar to winglets, which are widely deployed across the US airline industry. And we're a drop-in retrofit or a factory installation, which would get airlines their money back in about 2 years. Now, I said before that we're applicable to a wide variety of combustion systems. And just like we have jet engines, we also have gas turbines for power. So here at Argonne, we've been working with Capstone Microturbines, the largest producer of small turbines for distributed generation of power, to retrofit their engines with our technology. So they were interested in the emissions benefits and the fuel flexibility improvements that we could provide. And we're building up to a full-scale test on their turbine at the end of this year. So basically, the small improvements that we can make, the improvements we can make on this small system will help us validate our technology at the system level and be the gateway to a much larger market, which is the aerospace industry. Overall, we intend to have essentially the same relationship we have with Capstone with a couple other OEMs, right? Essentially, where we don't want to make the jet engines, we don't want to make the fuel injectors, we don't want to compete against all of the established knowledge and all the established engineering that there is in this field. We just want to take what we know a lot about, which is plasma-assisted combustion, and improve everyone else's fuel injectors just a little bit, and essentially exit the market via an IP transaction. So we think there's about a $2 billion per year market for this technology. Right now, we're raising a $1.4 million seed round for this technology, but we've also raised about $1.1 million in grants to date. We've done tests both at Case Western Reserve University, where I did my undergrad and graduate work, and at NASA Glenn Research Center. With Argonne, we've been working both on a high-pressure combustor that we built, as well as this Capstone turbine that I mentioned earlier. And our seed round would primarily fund the development of a customer site demo, essentially the first retrofit kit of our technology on a Capstone turbine. In parallel, we have 2 SBIRs that are funding control system work and a little bit of the jet engine side with strong collaboration from engine manufacturers. So it's not just me working on this. I'm supported by a great team. We're all aerospace and mechanical engineers from Case Western Reserve University, MIT, and Notre Dame. And we're also looking to hire 2 additional technical staff with our seed round. And with that, I'll take your questions. Actually, no questions. After the break, I'll take your questions.